to a fault-tolerant quantum computer. So thank you all for joining, and I'll just share screen right now. So let's just start the session. If we can record and I can start sharing so that we can present and go forward. I think I don't have the option to present. So Balaji, is there a way to present?
Yeah, I'll make it. I'm sorry. Just making it. Just
Perfect, no issues.
yeah, I made it.
Perfect. I think I've got the option now. Can you guys see my screen now?
Yeah, we can see.
Absolutely good.
All right. Perfect. So thank you everyone for joining in today. So it's like I would like to give a brief intro about Zen for Quantum today. So as I was having a conversation with Balaji earlier, it's like we have to have that passion for quantum computing. So it's not just about a technology or we are amidst a revolution, but it's also quantum is also a way of life. How to live life the quantum way. So that is what Zen for Quantum actually I think is a good way to uh, living the quantum life. That's what I like to say. So our talk today is focused on fault tolerant quantum computing, as I said earlier. So I'll just start presenting now. I'm the president at OneQuantum Bangalore. So if you're in Bangalore, feel free to reach out and we can have a good discussion. So who are we? Basically, it's a quantum community that works to advance the field of quantum computing. If you are a researcher, if you are in academia, if you are working in within industry, we are here to help you. We have the resources, we have all the connections to make you successful in this field. So that is what One Quantum Bangalore stands for, and I really appreciate everyone to try to get this word spread out as much as possible. So where are we actually? We are amidst the NISQ era, which is the noisy intermediate scale quantum computers, which have about 500 to 100, about 200 qubits at the present, but they cannot do much because we need a millions and billions of qubits to actually make these computers useful. So right now, IBM has a 127 qubit quantum computer, which is the maximum qubits, but there's different approaches to how we can make a quantum computer. There's actually about photonics quantum computers, then there's going to be superconducting qubits, then there's going to be ion trapped. So we don't have a clear idea as to which is the best technology at the moment, but there are opportunities for one technology to be better than the other, and that is what we are going to discuss today. So if you have any questions, just feel free to reach out and I'm here to answer all your questions. So first of all, just a little bit introduction about bits and qubits. So as you all know, bits are basically classical computing. We use them in classical computing. It's 1 or 0. So the switch is either on or it's off. So, but in terms of quantum computers, we have a superposition where the state of the computer can be in either 0, in between 0 and 1. So it's in a superposition state, and we can entangle different qubits with each other, so they have a connection between them, which allows infinite possibilities that we haven't even thought of yet. So like in transistors, we have, suppose if we have a billion transistors, we need to actually double those number so that we can reach to 2 billion transistors. That is going to increase the power of that whole chip with transistors by a twofold increase. But in terms of quantum computing, in order to increase the computation power by by twofold, we actually need to add 1 qubit to it. So that is the power of quantum computing. It is the exponential power that it has, and it's a totally different way of computing with respect to classical computing. So that is where the power and the computational to such an high extent we can see, and we can use those quantum properties, we can harness those properties to make an actual quantum computer. So it doesn't matter which approach we have, it's either fault or it's either photonic, it's either superconducting or ion trap, but we can make these quantum computers that are way more powerful than classical computers. So that as they say that in the past 60 years, whatever progress we've made, we need to make that similar progress in quantum computers in the next 3 years. So that is the time frame we are considering, and that is a huge statement in itself if you try to consider what we've achieved in the past 60 years in terms of semiconducting industry and how fast we've grown. That's going to be quite an achievement for us to for mankind to achieve such a goal in the next 3 years.
Absolutely, Manan.
So
As I said
quantum
in the beginning, Manan, can I just
yes,
interrupt for a moment, a comment? As I said in the beginning,
yes,
exactly the time it took from the first ELIZA AI program to make AI very comprehensible and commercially available, and almost everywhere now we see it has invaded our lives, our, I would say, systems, everything in terms of whether it is supply chain, logistics, technology, anywhere to the tune the programs we watch on our regular TVs, everywhere we see predictive modeling, and everywhere now. Initially, when we started with those arenas, knowledge was power. Today, we say data is power because data churning allows us basically to generate all this modeling and then make predictions and everything. Now, in terms of exactly as you said, that advent which took so many years because of the limitations in the hardware side and other availabilities, now that has been overcome, and absolutely this time it'll not take 25 years, it'll take maybe 3 to 5 years. We absolutely agree with that. Yeah.
yes, definitely. So it's as quantum computing, we have this first movers advantage where we can try to, as you'll
Yeah.
see, it's a steep curve, because the people that start, the organizations that start today are going to have an advantage over the other organizations that do not start today, and it's going to be very difficult to build an in-house quantum center of competency. So it is also going to take a lot of time and resources in order to build that. So that is why it is essential for organizations to start early, and there's application in all the industries, be it healthcare, material science, finance, and AI. So it's going to be who starts first so that they can have that advantage in quantum computing.
Correct.
So I'm going to discuss about the advantage. What is the quantum advantage? So firstly, we have a problem that has no fast classical algorithm, and it has to be a useful problem which also has a fast quantum algorithm. So we have to target the middle over there, and we need to think about the system size, what is the time to solution, and a little bit of other resources, which is all proportional to a times n, which is exponentially raised to the power beta. So that is what we have to think about in terms of getting that advantage, the quantum advantage. So it can be an exponential advantage, or or improving the polynomial prefactor, which is going to be a polynomial improvement. So I'm going to discuss how it is. So suppose we have over there in terms of n, and we try to reduce that expression into n raised to the power 1 by 2. So that is going to be a polynomial improvement. And for an exponential improvement, we'll have to think about, suppose there's the expression is 2 raised to the power n, so we'll have to bring it down to n cube. So that is an exponential improvement in the algorithm. So that is what we can do with Shor's algorithm, with Grover's algorithm. It brings down the time it takes to solve that problem. So that is why we need to focus on the center, which is we have to have a fast algorithm, a useful problem, and no fast classical algorithm to be able to solve that problem. So what is exponential power? Actually, it's like, suppose we have 1 penny, 2 pennies on the first day, and we keep on doubling the pennies each day. So how many pennies are we going to reach on the 31st day? So it's actually over 21 million penny dollars. That is the power of exponentials. And consider this penny as a qubit. So think about how much exponential advantage we add by just adding one more qubit to the system. So it, because it increases the power of the computer twofolds, it's doubling it. So it's a huge statement in itself, because I think the power is still underestimated by many sectors. They're still not transitioning into quantum computing because they don't see the real value. But considering how important it is to start early, and considering all these advantage, it is very essential for countries, for organizations to start early and try to adopt this technology into their use cases, their business use cases, and try to bring a value to the company. So suppose we have a problem. So it's not about solving every problem. So suppose you have a calculator on your phone, right? So you don't use that to solve 2 into 2, you know that. So that is where quantum computers, they are not going to solve ordinary problems which we have answers using classical computers. They're going to solve problems that are not solvable. That is where we are thinking right now. And suppose we have a quantum computer with 30 qubits, so we can simulate that on a laptop. But if we had, for example, 80 qubits, that is going to take all the computers on earth, and that is going to be the size of the simulator. Now the computational power, if we have just 300 qubits, that's 300 logical qubits, that is going to be greater than the number of atoms in the whole universe. So I think it's going to be like 2 raised to the power 300. So that is a huge number in itself. Now coming to the producer and the consumer divide. So there's a lot of quantum producers right now, but the consumers are very less. But very soon we see a transition where the consumers are going to explode, but there's going to be very less quantum producers remaining. So it's early. It's very essential for organizations to start producing quantum related software or hardware so that they can have an edge over other businesses. So right now, as I told, we are living in the NISQ era, which is the noisy intermediate scale quantum computers, which have a very less number of qubits, but we can still solve a lot of problems with them. We can still try to solve a lot of problems with them, be it modeling cars, be it trying to discover a new drug, simulating H2 molecules. We can do that, but it's not up to the mark because there's a lot of errors in these kind of computers, and that's where the term noise comes in. So we have seen, I hope you have seen the IBM system one, which is placed in Germany. It costs around $40 million. So it has a 127 qubit eagle processor. So it's kept in the same glass where the Mona Lisa is kept, the same glass inside the Louvre. So it signifies a historic or a unique kind of achievement in the history of mankind, where we're trying to compare it with the same glass that is kept in the Louvre, which holds Mona Lisa. So it's a 127 machine, beautiful machine, and it has the capability of doing some wonderful calculations. Then I think you've heard of the term quantum supremacy, where Google tried to come in with the Sycamore processor. They tried to claim that it's faster than the classical computer, where it could do a calculation, a random calculation in about a few seconds, compared to the same calculation if we did on a classical computer, it would take 10,000 years. So that is where how fast we get to know how fast these computers are. So it's a 54 qubit chip, and it try to have a million samples, and these are the type of structure that we need for a quantum computer, which has the amplifier and attenuators, the wiring, the dilution refrigerator. So this whole structure is for a superconducting quantum computer. So I'll come to different technologies later on. So feel free to
Yeah.
have ask any question that you have.
Manan, for our, I would say, audience, if you want to give them a sense of kind of super cooling and what kind of increased challenges and costs are involved for these computers? Give them a sense of that as well, why this is still a challenge from that angle, affording quantum computers, physical quantum computers.
Yes, yes, so these are very expensive machines. They cost millions of dollars, and it's the same with building them. So it's going to take a lot of resources trying to build these machines, trying to come up with new processors. The whole cycle goes on, and that adds to the cost. So these are very expensive machines, and they have a processor. So they have one processor, a whole lot of boxes and mounts, then the wiring is there, so we send microwave signal down those wires that reach to every individual qubit. So we send microwave signals to the qubit, and they are kept at very low temperatures, which is colder than outer space. So it's millikelvins we're talking about over here, and one of the most coldest places in the whole universe. So yeah, and we've come to that point where we can do that in our lifespan. So yeah, this is very cool. We try to, because these quantum effects are observed in these type of temperatures in terms of superconducting qubits. I hope that answers the question.
Thank you, Manan. Yep.
Perfect. So we'll be moving on. Then we have a whole debate between IBM and Google. So they have their own claims about quantum supremacy. So IBM then claims about the same quantum calculation that we can do that in 6 days. So there's no 10,000 years. It's just that we can do that same calculation in 6 days if we had a 128 petabyte SSD. So they store that, and it's a random calculation. And these machines, so one of them has the Schrodinger Feynman machine, the other one is Schrodinger. So it's like a different kind of a claim that IBM is making now. So that is the difference between how these companies are competing with each other as to which is the fastest, which computer is the fastest amongst them. So coming to a brief overview about superconducting QPUs. So this is how we build them. So this is actually the only quantum element of a quantum computer, because we have these wires that are of the classical realm, but this is of the quantum realm. And how we can try to make these qubits. So IBM has their own software with, it's called Qiskit Metal. So if you guys are enthusiastic about building these circuits, you can just try out their application and try to build some of these superconducting qubits. And they have this whole 3D stack where we try to place the qubits on one stack. So it's flip chip bonding, and then we try to place the readouts on another layer, and the connections between them on a separate layer, which is called the interposer layer. So this kind of a 3D integration we are seeing in the quantum processors of the superconducting qubits. But the question that we need to ask ourselves is, does this mean that it is the road to a fault tolerant quantum computers? We are very soon going to find that out. So this is, as I talked about, the qubit and the interposer and the readout layers between the quantum qubits. Does anyone have any questions up till now? I hope this has been an interactive session up until now. Anyone has anything to say? Any questions? All right, then we'll be moving on towards our next cryogenic systems. So Blueforce is one of the major manufacturers of the cryogenic systems that are used for these quantum computers in the modern era. So they have a cryostat, a compressor which cools down the temperature of the cryostat. Now we're going to come to fault tolerant or error corrected quantum computers. So can we scale these superconducting qubits to millions of qubits? That is a question that I'm going to answer today, and which I think, for useful quantum computing, we need a manufacturable technology, a fault tolerant architecture, and a realistic path to scale. So these quantum computers have errors in them. And in order to mitigate these errors, we need a lot of qubits in the range of millions, as I told earlier. So we can have the quantum advantage with algorithms like QAOA or VQE for the near-term quantum computers which are used in the NISQ era. But in order to apply Shor's algorithm, we need millions of qubits. So how are we going to reach that kind of a stage, and what solutions we are going to need? So in any experiment, we have noise, and this is what an ideal experiment looks like. So suppose we have to apply the X gate on a qubit. So this is what happens. It changes the state from -1 to 1 and back and forth. And this is how many depth we have in the circuit. And suppose if we run it on an actual quantum computer, we are going to get this result. So this is due to the coherent noise, the incoherent noise, and the projection noise. And this is the actual reason why we don't have a useful application in quantum computers yet, because they are very noisy. So how can we mitigate these noises? What is the architecture we need to follow for fault tolerant quantum computing? We can try to build the CMOS architecture where we have these wires. We can try to reduce them and place them next to the qubits, which is going to increase, and we can try to leverage the power of the semiconductor industry and try to develop the control systems as close to the qubits as possible. And we don't need microwave wires for that, but that is still an actual area of interest where researchers are trying to do their best to get that level in superconducting qubits, and we can make these large computers with such big chandeliers as small as possible. But considering a different approach now, all right, where we can try to develop ion trapped quantum computers instead of superconducting qubits. So this is a different approach now we are using, where you can see those blue dots, that every dot is actually a qubit. So we don't need the qubits that are manufactured on on a semiconductor chip. We can try to make these in a different way, which is the ion trap quantum computers, and we can then connect these quantum computers together. So suppose we have 1,000 qubit quantum computer, ion trap quantum computer, then we can connect it, and then we can have a 2,000 qubit quantum computer. That can be done using optical fibers, the same fibers that are used in your routers, in your modems. And this means that we can actually scale these quantum computers to an extent that 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 we need in this era, where we can solve some real valuable problems. So that is a different approach, as I spoke, from the superconducting qubits. This is ion trapped quantum computers. So I think, in my opinion, I think this is a much better approach towards scaling these computers, and we don't need the same temperature. We don't need to store them at such high, at such low temperatures. We can use them in the normal room temperature. So that is an advantage that they have, and they are very high fidelity. They have, obviously, they have higher decoherence times, and the gate speeds is comparatively less, but it still means that we can really get to that level of logical qubits where we can solve valuable problems. But there is
Eh,
also a different approach to that.
so Manan,
Yes, I heard some noise.
definitely, as you said, this is like eliminating the need for super low temperatures. And does it eliminate also some cost in terms of cost reductions going through this approach? Or that's even,
Yes,
so that would be
definitely.
good.
So we don't need such kind of cryogenic chambers for them, so that definitely decreases the cost. So I think it is going to be a much more preferred way in the long run. So for now, we can use some superconducting qubits to solve problems, but for the longer run, we are going to need this technology. And I think all the experiments we talk about in terms of, be it the Young's double slit experiment, so it involves some kind of photons and lights in them. So it's like photonics is the way forward, and be it in terms of ion trapped photons or photonic chips, I think this is going to be one of the key technologies that we can leverage for developing fault tolerant quantum computers. And just the fact that we can connect them and they can be interchip entanglement between them, it is a key differentiator.
So, Manan, for the benefit of audience, give them some general applications. I think you may be going there. Maybe I asked a question right, Nick, ahead of time, just to give them
Yeah, no,
a
no worries.
connection between where we are in this technology which we are discussing and what kind of problems, and also in terms of fault tolerant system, what kind of real life, real time fault systems which we are intending to solve using this technology so that they can connect better in terms of the discussion.
Definitely. So we have application in every field, be it machine learning, be it the metaverse, be it blockchain, cryptography. The applications are endless. And for me, I think it's about how we can try to optimize the supply chains and then predict weather patterns. So everything is going to be impacted by this technology, and how we can send signals that are much more secure using quantum encryption. And this is why we have applications that are ranging from each and every sector, from defense, we have finance, then we have automotive, where we can try to develop better bodies of car. And suppose I'm going to give you an example over here, that for the F1 industry, we have a car, and we have a lot of cars for the race. So for example, if one of the cars applies quantum computing to them, they are going to have an advantage that no other car has, because they have a better body, that makes the car faster. And the 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 other cars that are still following the classical approach won't be able to catch up with them, because they'll be able to create new materials, newer designs, that is much more efficient and faster than the other cars, because that is the speed which we can achieve quantum supremacy. And I'm going to give you another example over here. For example, in terms of autonomous cars, so we have to place the sensors, right? uh, the lidar sensors, then the cameras in
Yep.
that autonomous car at a certain angle and at a certain position. Now if suppose we have 4 5 cameras, or maybe a lot of cameras that we have to place on the car, where can we place those sensors so that the car performs at the most optimal way? So we have to place them at a certain angle, and then we have to place them at a certain position in order to achieve that optimal value. And that is where we can find infinite number of possibilities which are impossible for the classical computer to solve. And that is where quantum computer comes in and tries to solve that problem in an exponentially faster way. And still we have to develop those algorithms, still we are in that process of getting that advantage which we haven't had in the past few years. So there's this buzz in the industry, but we still need to get to that actual advantage where we can simulate molecules, or try to get that uh, the or try to get our supply chain optimized. So we still haven't got there yet, but it's still a long way to go, and we are at the beginning of the journey. And one way to get to that quantum advantage is obviously photonic quantum computing, which is highly manufacturable. So just like we have the chips in our systems right now, we can try to integrate quantum computing into those same chips, and we don't need those low level of cooling. And that is possible with photonic quantum computing, which have a very atomic scale fabrication, and they also have predictable performance, and they don't have any heat, as I told. And in these systems also, we don't require any transducer, and which means that interchip teleportation is possible between these quantum chips. So I think these are also steps to a fault tolerant quantum computer, and they have an advantage to ion trapped and superconducting quantum computers because they are accessible, they are scalable, and they are highly versatile. These 3 points make them a very unique approach in quantum computing. So if I were to place a bet on which technology is going to be reaching quantum advantage the fastest, I would be placing my bet on photonic quantum computing.
So, not to take
Because
away
as
time from from our main subject in terms of fault tolerant systems, which we are discussing, and as you said, some of the applications definitely involve manufacturing and supply chain, and we all know supply chain industry is facing real good problems nowadays. In what way can you visualize, and for the sake of like quick answer, not to take too much time, but these kind of systems can help in, at least it may not immediately solve the problem, but it may help us avoid this kind of situation in future. How can we basically go that path? That's where my precise question would be, using this technology.
yes, so there's two problems I'd like to discuss. One is the traveling salesman problem, and the other one is the knapsack problem. So, suppose for the logistics, we have ships going across the oceans every day, right? And these
Mhm.
ships have to carry a certain amount of weight, and each item that they have in their inventory has a cost. So how can we find the optimal route from one city to the other with these ships that is still not solvable using classical computers? We have heuristic methods to solve these kind of problems, but we don't have an algorithm that can solve this on classical computers, because as we scale the number of depots and the number of ports and the number of ships, the problem's complexity increases exponentially. And I think that quantum computing can be used to solve this problem in a much more faster and efficient way, because the qubits can be providing real advantage in terms of the classical bits and transistors. So this is for the traveling salesman problem, optimizing the route. Then there's also the problem of giving each ship the certain amount of weight and the certain amount of materials for them to carry. This is where the knapsack problem comes in. And I think this problem also can be solved using a quantum computer. So these are certain advantages that we can try to leverage. So every industry, if suppose you are in the logistics, be it FedEx or any other organization that wants to optimize the supply chain, this is the way forward. Quantum computing is the way forward. And I hope that answers your question, right?
Definitely, man. I think that that was absolutely to the point. And I believe I'm taking this discussion to another interesting level, where we normally say, and I believe most of the people who are from India and who have been traveling, for example, from India to US and back, at least last 25, 30 years, we have not seen any reduction in the flying time from India to US. Do you think any of these technology, as you was talking about the cars and fast running cars, what kind of scale of economies in terms of time can we expect putting this kind of technology to use, and would that reduce the time travel? I know we have some supersonic options available, but they are still not making big difference in terms of the time to travel around the globe. Where do you think this can help?
So in order to travel faster, we are going to need materials that are much more lighter, and a shape of the aerospace has to be such a way that it increases the aerodynamics. So I think this is where quantum computers can come in, trying to make the shape better, than trying to, you know, make the speed faster using these uh, using the quantum computers, because the body, if the body is lighter, if the body is much more aerodynamic, these aero these airplanes are going to travel much faster. So this is where we can try to leverage this technology and reach from point A to point B in a much faster way. And this is one aspect. And the other aspect is in the aerospace industry, we have flights going on from point A to point B, then point C. So how we can optimize the route in such a way that the tourist does not have to wait for a long period of time in order to travel from one point to the other. So it's not just about developing better materials, it's also about optimizing the whole route of these these airplanes. That is where I think quantum computing is going to come in.
Yeah, I
Thank you.
agree with that point. Good point. Actually, to add that, even the universe itself a quantum computer, and it manufactured the biological system. If you say, I mean, take I'm from biological background, and if you take the ants when they move, how they root themselves in without clashing each other. Recently, they did a research on ants, the small insects, how they take their goods from one place to other without clashing with each other, because they have a very big community. When they carry things, they should not clash with each other, but they know how to navigate very systematically and do that. So there is some quantum level going on in biological system also. Even our thinking, brain neurons, everything operates on certain biological level, chemical level,
Yes,
quantum.
that's agreeable. I think that at the smallest level, it's all quantum, where we cannot differentiate. But because I believe that our brain is a whole, neural networks are there, so it can be called a quantum computer. And we can also say that I read an article recently. It said that we are living in a simulation of quantum computers, which I believe it's not true, but to some extent we can simulate the world using quantum computers. So it's just about a coin toss, for example. So whenever we toss a coin, we know it's a random event, right? Tossing a coin, it's going to end up 50% chance is heads, 50% chance it's tails. But if we know the weight of the coin, if we know the structure of the coin, if we can simulate that coin toss, if we can simulate the air in which we are tossing the coin, we can actually predict what is going to be the outcome of that coin toss. So for example, if we can give the same data, the 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 actual data to a quantum computer, it is going to predict the coin toss to an extent which is going to be actually true, which cannot be done using classical computers. So that is where, uh, as I say, quantum computers have the potential to be a national threat to countries, and also a foundation to future economies. So that is the potential that they have. They can transform the world in unimaginable ways, and make a country much more economically stronger and compared to different countries. So it is also important for the countries to start acting in this industry at a very high rate, because that can provide advantage to their people, to their communities, to each and every individual living in the country.
Thank you.
I hope that makes sense.
Yes.
Absolutely, I think, yeah, let's continue further.
Perfect.
Uh,
So any practical path to a million qubits? Yes.
Just a second, Manan. I think somebody was trying to ask a question.
right.
Can
So, yeah, Chandrika, this side, Manan, I have a question for you. So, while you were discussing, different architectures for quantum and discussing the path forward in terms of scalability. So, in recent news, Microsoft announced, advancements with topological qubits. So, any, comments on that?
So yeah, I think it's a new way. They have obviously been researching for a lot of years in topological qubits. Now they've actually realized that topological qubits are a new we can harness that computing power to create a quantum computer. So still it was in the research stage earlier on, but now it's actual reality. We can make, and very soon we are going to expect a quantum computer from Microsoft. I think they have moved into that phase now with their research level. So it's going to be interesting to see how, because in topological qubits we are also leveraging the semiconductor industry. We are trying to integrate a small photon or an electron between those, just like we have the transistor where we have the drain, where we have the input. We can try to put that electron into that space and develop a qubit out of it, which has an upspin or a downspin, which is very, I think it's a great breakthrough from Microsoft. And if they can use this technology, they can we can have a lot of potential in getting to fault tolerant quantum computers.
Okay, thank you.
Perfect. So yeah, but it does not mean that the number of qubits that we have, the physical qubits that we have is going to be proportional. Or let's say, suppose we have 10 10 logical qubits, so we have to multiply it by 10,000, and then we are going to get the physical number of qubits. So we are still very early. I think it's going to be take us a lot of while to reach that level. And just hold on a minute, I'm having a meeting actually, I'll get back to you later. So the number of physical qubits is directly proportional to the number of logical qubits into 10,000. So that is the industry preference right now. So in the near term or the medium term, we are adept to solving problems that include applications for machine learning, for search and graph problems where we have to find the optimal solution, or simulation. So the applications are endless, and it's just the beginning of we exploring these applications. It's in the field of chemistry, machine learning, encryption, every, you name any industry, quantum application is going to be there. So in finance, how we can predict the price of stock, we can do trading very fast, we can do fraud detection. In every industry we are going to find the advantage in quantum. So if you have a business, you need to transition uh, into quantum computing as soon as possible. With that, I need to say that the best time getting into quantum computing was 5 years ago, and the second best time is now. So if we are ready to delve into the quantum realm, we are going to find answers to questions that were never possible. So that is why we need to think about getting into this technology and getting that head start as soon as possible. With that, I'd like to end the presentation. I want to thank you everyone for joining. If you have any questions, feel free to ask them now.
Any questions? I would request audience, please introduce yourself quickly, 30 seconds, and then ask the questions.
Yes.
Hey, hey Manan, Rahul this side. Do we have the recording of this session available?
Yes, we will be posting
Uh,
that recording.
Okay, thanks. Thanks,
yes.
Manan.
So I have another question, Chandrika again. So when do you see the inflection point for quantum? Though I understand there are many challenges at the moment, error correction, increasing the number of logical qubits, etc. But in which year do you predict, for us to have a fault-tolerant large-scale quantum computer which can do meaningful applications?
So I think that answer depends on the industry. It depends on the kind of people that are working in the industry. So there's a talent shortage going on right now in quantum computing. So it's about getting more and more people to know about this technology, then trying to make them understand about this technology so that they can transition into this technology very soon. So it depends on a lot of factors. So I see personally, I see reaching that level in the next couple of years, where we can actually see business use cases developing in quantum from the NISQ era. So it's not very far. The actual use cases, we have commercial quantum computers being developed by IQM, by Rigetti, by IBM, which obviously are providing some kind of advantage in some small areas, some niche areas. So the actual advantage is already beginning to be showed up from the NISQ era quantum computers. And as we reach the NISQ era, I think it's going to be very important for industries to transition their security systems, for countries to transition their security systems to an architecture to fall to where it's unbreachable by quantum computers. So the sooner they start, the better it is, and it's going to be very important for the next couple of years are going to be very important for the quantum industry as a whole, because IBM has a roadmap of developing 1000 qubits by the end of 2023. So I believe that 1000 qubits can solve problems that were previously unsolvable by classical computing. And I would also like to mention out one small point over here, that these quantum computers are not going to perform well without the classical computers. So it's going to be, the future is going to be a hybrid classical quantum computers, where the quantum computers are going to be in conjunction with the classical computers or the HPC computers. So if we're going to talk about this this technology as a whole, then HPC has a much bigger role to play than quantum computing for now.
Okay. My name is Ying, and thank you very much for your great presentation. Manan, I hope I say your name correctly. Two questions.
Yeah.
One is about photonic quantum computing. Maybe more. Or second question is regarding, I think Dr. Galatro also asked about that path to million qubit. Both questions will be related. Yeah. I'm going to ask the first one first, regarding photonic quantum computer. Maybe just from the very basic term, you mentioned, say, photon do not feel heat. I think that's much more, that's more compared to electronic, right? So very basic, from physics perspective, why photons do not feel heat while electrons do.
Well, I think that's down to the chemistry level. I think photons have a property. They have a duality property where they can act as a wave or as a particle, where an electron acts just like a particle. So I think that is why they are unique in themselves, and they cannot they can possibly have sustainability with heat. I think that is why what differentiates them. So I'm not a researcher into chemistry, so I might not be the best one to answer that question, to be honest. But I do have an idea that photons are much better in terms of sustaining heat.
And then you think that's the reason why for the photonic quantum computer do not need the super low temperature.
Yeah.
Do you think that's the reason?
That's correct. Yeah.
The other one.
Yes. So in superconducting qubits, we have the pads. So if I had edited out the presentation earlier, but if I could show you the actual processor of a quantum computer, which a superconducting quantum computer. So we have two pads, and between them the pads we have a layer which is called the Josephson junction. So that Josephson junction, using that junction we can transmit the Cooper pairs of electrons from one end to the other. So we are having electrons over here but compared to photonics, we have just photonics over there. So that makes them, and in order to make those Cooper pairs go from one junction to the other, we need to cool them down to that temperature. That is why we need to sustain them at low temperatures.
Mm-hmm. Back to that that you just said regarding electronic regarding electron, that could electron could behave as a duality as well, right? Particle and wave, not necessarily just only particle. It could be also behave
So
wave, isn't it?
I think electrons have mass, so they don't behave like wave. So as I
Not
told,
at
I'm
all.
not the expert on quantum chemistry. I had some experience in my high school, but I don't think that electrons have the same property as photons, because photons travel at the speed of light, whereas electrons don't due to the mass that they have. So I think that is why we need to cool them down, and we have such an architecture in photonic quantum computings where we don't need to cool them down.
Okay. Second question was related to what Dr. Golacho also asked you regarding that any practical path to a million qubits. Um, it's also this is also related to quantum communication. Of course, with the quantum communication is different than a quantum computer, but with a quantum computer with satellite that can now is over 1,000 kilometer. That is that
Yeah.
connection. So as I mean, with that currently with satellite, does not need I think earlier you mentioned also about optical fiber, con you know con you, you know trans connection and semiconductor industry. Um, what with your experience or with your knowledge with photonic quantum computer, how far so far that can those you know um, pass even with
So
go ahead.
So with photonic quantum computers, I think the time frame that we can consider is still about 3-4 years, because with them we don't actually need to develop those low level systems with 10 qubits or 100 qubits. We can actually develop a million qubit quantum computer without actually trying to develop these slow state systems where we try to scale them up with 100,000 then 100,000. We can actually develop them straight away. So there's a company called Quantum that claims to do that. So I've researched about them, and I think that they have this structure as I uh, outlined in my talk regarding photonic quantum computing, and they plan to do that in the next 5 years. So let's see what's going to happen in terms of, it's going to be a unique race between all these technologies, and we need to see how we can get to that technology faster. But coming back to one important point that I would like to mention is how India can play in this technology, because we should focus on our strengths, which is the software. So I've seen India investing and India trying to come up with a scheme of semiconducting manufacturing, but our key strengths lie in software, where we can try to develop new software for this technology, which is not dependent on the back end. It doesn't depend which technology we use. It's either photonics or superconducting. What we can do is try to leverage our own ecosystem of programmers. We have such good people that are into computing. If we can try to upskill them, and I think OneQuantum Bangalore can highly benefit from trying to upskilling those people into quantum computing, and so that they can take that quantum leap and try to develop software that is actually useful for the country. So that is where our organization comes in. So if you are in Bangalore, feel free to reach out and I'll be happy to assist you.
Thank you. When I asking how far I didn't mean ask how far will that to come. I meant to ask how far from your experience, how far that with the photonic quantum computer, how far that can travel. I know, I mentioned earlier with quantum quantum communication, but even with quantum with optic fiber, whether it's quantum communication or quantum computer through optic fiber, that signal, weakening.
That signal, I think.
Yeah,
I think I got your question now. It's about QKD, right? Quantum key, where we can try to signal from one point to the other. The how we can effectively try to send that signal, which is not encrypted in any way. If that's what you're trying to know. So I don't.
No.
I think you're
Actually,
in quantum communications, right? This question is
no,
related
I'm
to
not.
quantum communications.
I was not asking about the encryption perspective. I'm asking about the signal will decrease exponentially when the physical distance increase. So that's what I'm seeing.
Yes.
With the optical fiber, with that node, that could be also some encryption challenge there as well. In
Yes.
addition,
So there's going to be some challenge as well, but to that extent I'm not the expert in that area, so I won't be able to answer with that much accuracy. But I think that with the increase in area of the signal, the quantum properties are going to decrease. So that is what I would like to say. I think that's going to be the what's going to happen, because we have researchers in India testing out QKD up to certain kilometers, but that is the level that they have achieved, and they're trying to increase that level. So it's a few thousand kilometers, and now they're trying to achieve more and more. So it's better to achieve that long distance, because we can then transmit signals that are quantum secured over that distance. So which means that if any listener tries to interfere with that signal, the wave function is going to collapse, and that means that our message is as secure as it can be. And as we increase the distance, that means that it is more difficult to send out these signals to the receiver.
Okay, great. Yeah, thanks again for your great presentation.
Thank you so much, Ying. It's a pleasure to have you today. So
Thank
if
you.
anyone has any other questions, just feel free to ask me. And if you still want to reach out, you can connect with me on LinkedIn, and I'll be happy to answer your queries. So yeah, I feel free to reach out on LinkedIn. So I'll be happy to help answer any questions that you have.
Any other questions for Manan, guys? Any other questions? If not, then I think we can wrap this presentation. Thank you very much, Manan, for this great presentation. I know it's late for you, almost like midnight. Thanks a lot.
Yeah.
And if you, as
My
Manan
pleasure.
said, feel free to reach out to him through LinkedIn, connect with him, and we can go on from there. And then in future, we'll be back on the same channel with you guys with another presentation in the area quantum computing. Over to you, Balaji. Take it over.
Thank you so much, Virendra.
Manan, for a wonderful talk, and it was very insightful, and a lot of gaps which I had in the quantum field, it filled some extent. Still gathering a lot of information. So next week we have another, not next week, next month, we have another speaker from India. So we'll continue our Saturday talks as usual. And thanks, Virendra, for coordinating and moderating this event. And I will open the floor for the participant to ask questions. At the same time, networking, they can share their information and come up with ideas about for the next talk. If anybody has any recommendation from that circle who can give a good talk, like Manan did. So it was nice of you, Manan, and with a short notice you are able to do. I was surprised when you say within a week you are going to deliver this talk. Yeah, it was really fantastic, and I like your the PowerPoints which you presented very neatly, and each content is very clear and very nice. If you have time to share the PowerPoints, that'll be good with the members. That'll be I can circulate that too.
I'll be happy to do that. Thank you so much, Balaji, for having me here today. It's been a pleasure to interact with you all, and I hope to join this session again very soon. So thank you everyone for joining in. Have a good day for now.
Thank you.
Thanks a lot, everyone.
Thank you, Virendra. Thank you, Balaji.
Thank
Bye
you.
bye.
Good presentation, Manan. Thank you.
Thank you.
All right. Guys, as Balaji said, the formal presentation is done. Balaji, you can stop recording at this stage, I believe, beyond this.
I'll stop that.
Yeah. And